Welcome to all of you. First of all, I'd like to thank you for 500 subscribers. Before starting today's set videos, I would like to say something to those who are working very hard for different competitive exams. So we have a couple of exams ahead, like TIFR, which is called GSO 2019, NET, CSR NET December, GATE, JEST, then BRC, and more exams are there. So this is October now, so not much time is left. Now you all are at different preparation levels, and some of you are preparing in a well-planned manner, and some of you are preparing randomly without a proper planning. So I want to say you that take couple of hours and look into your preparation, how much you have finished or how much is yet to complete. Make a proper plan for this 2 or 3 months and be focused, otherwise you will have to wait for another year with great regret. So be careful, make a proper routine, plan your study hours, and try to practice as many questions as possible. So let's start today's set video. So today is 7th of October 2018, and this set 13 contains questions from Solid State Physics. And the first question reads: consider electrons in graphene, which is a planar monoatomic layer of carbon atoms. If the dispersion relation of the electrons is taken to be Ek equals to Ck, where C is a constant over the entire K space, then the Fermi energy Ef depends on the number density of electrons rho as. So this is a very easy question. So dispersion relation is given. So Ek equal to Ck. Now in 2D, because the question is asking about graphene. So graphene is a plane structure, so it is in 2D. Graphene is basically a sheet. So density of state in 2D in terms of wave vector G, wave vector is written like this: Gk dk equals to 2 into L by 2 pi whole square 2 pi k dk. This can be written in 2 dimension. If it is in 3 dimension, then we could have written 2 into L by 2 pi square or cube, maybe cube, into 4 pi k square dk. Okay, that I will check and let you know if some confusion arises. For 2 dimension it is written like this. This factor of 2 has been included because we are talking about electrons which had spin up and spin down. So this dispersion relation is given, so from here we can find out k and dk as well. And upon putting, so here it is written in terms of k, so now we now want to replace it in terms of energy. So GED equals to 2 into L by 2 pi whole square 2 pi, and in place of k we have written epsilon by c, and in place of dk we have written d by c, and as a result of that we get L square by pi c square epsilon dE. EDE, number of electrons at t equals to 0 Kelvin is, so FeGD. Now Fe means probability of distribution function. Fe is 1 at t equals to 0 Kelvin, so we have not shown here. So 0 to EF GED. Now GEDE and these constant terms are coming outside, and therefore number of electrons n is found to be L square by pi c square EF square by 2. So from here EF square equals to this. N by L square means number per unit area. Number density means number of electrons per unit area. We are writing it as rho. Rho is given, so number density is given. And we find that this term is constant, so EF is proportional to rho to the power half. So option 1 is matching the criteria. So option 1 is the correct option. Now coming to question number 2. Suppose the frequency of phonons in a one-dimensional chain of atoms is proportional to the wave vector if n is the number density of atoms and c is the speed of the phonons, then the Debye frequency is. Now this dispersion relation omega equals to ck is given. Now in one dimensional it is asking about one dimension. So one dimensional gk dk equal to L by 2 pi into dk. Okay, so we have to write in terms of omega because we have to find out frequency. So g omega d omega is L by 2 pi and dk. So this dispersion relation is given, so from here we can write dk as d omega by c. And number of electrons is found in the same way, 0 to omega d, g omega d omega. So L by 2 pi c omega d. So omega d equal to 2 pi c n by L. N by L means number of electrons, or not electrons, phonons, or number density of atoms. So number of atoms. So number of atoms per unit length. So number density. So 2 pi c n. So option 1 is the correct option. So question number 1 and 2 are quite similar. Now moving to question number 3. The band energy of an electron in a crystal for particular k direction has the form E of k equals to a minus b cos 2ka, where a and b are positive constant and 0 less than ka less than pi. The electron has a hole-like behavior over the following range. So this question is little bit informative, or what you can say, you should know the fact that when the electron shows hole-like behavior, so this dispersion relation is given where a and b are positive constant, and this is a range of ka given. The electron will behave as whole when its effective mass m star is negative. Okay, the effective mass m star remains negative for those k values which lie in between point of inflection, means d square e by dk square equal to 0 and top of the band de by dk. Now de by dk equals to twice b into a sine twice ka, and that should be equals to 0. So if you get to equate it to 0, we get twice ka equals to n pi. That means ka equals to n pi by 2, where n equals to 1, 2, 3. Now you can visualize the ek diagram. Okay, so this is the top of the valence band, and this is the bottom of the conduction band, and m star is greater than 0 here, m star is greater less than 0 in this region. So then this difference in energy is called band gap energy. Now another condition, d square e by dq square equals to 0. So you're taking derivative again with respect to k, we get this, and from here we can see cos twice ka equals to 0. So we are writing it as cos twice n minus 1 pi by 2. We could have written twice n plus 1, but n should be 1, 2, 3, so we are writing twice n minus 1. Okay, so n and this n are same. So from these two relationship we can set the value or range of k. So therefore k should lie between, look, this should lie between d square e by dq square equals to 0 and de by dq equals to 0. So this is the range. So from this condition we are getting this, and from this condition we are getting this. So k should lie between this twice n minus 1 pi by 4 less or equal to k less than equals to n pi by 2. Now we will put the value of n. So suppose we are putting n equals to 1. So pi by 4 less than equal to k less than equal to pi by 2. This is for first band, and pi by and if you put what n equals to 1, then you will get 2 or 2 to 4 minus 1, 3 pi by 4. So from pi by 2 to 3 pi by 4 for second band. So throughout this region we are getting hole like behavior. So combining these two regions we get pi by 4 to 3 pi by 4, and it is matching with option 1. So as you can see, E versus K, so A minus B cos K, twice Ka. So if you plot it, you will get a graph like this. So from pi by 4 to pi, 3 pi by 4, we get negative effective mass. Look, as I have already told you that there is a software in Google Play Store, Desmos. You can download that software so that you can plot any kind of graphs very easily. Now question number 4, the first order diffraction peak of a crystalline solid occurs at a scattering angle of 30 degree when the diffraction pattern is recorded using an X-ray beam of wavelength 0.15 nanometer. If the error in measurements of the wavelength and the angle are 0.01 nanometer and 1 degree respectively, then the error in calculating the interplanar spacing will approximately be. So we are given 4 options. Look, this is not 1.1, this is option 1 into 10 to the minus 2 nanometer, okay, and 1.3 10 to the minus 4 nanometer. Okay, so theta b is given 30 degree, lambda is given, delta lambda, delta theta all are given. So delta theta is given in 1 degree. So look, whenever in questions, in physics question, you are given something in degrees, then most of the time we have to convert it into radian for calculation. Okay, so here also we have done it. 1 degree equal to pi by 180 radian, because 180 radian equal to 180 degree equals to pi radian, you know. From that relation we get this. So what is the question asking? So they have given the error in measurements of the wavelength and angle, and you have to find out the error corresponding to interplanar spacing. Okay, so first of all we have to know the interplanar spacing, then we can calculate the error. So from Bragg's law we get this relationship, and from here we get d equals to 0.15 nanometer. Now we have to find out if the errors in determining these quantities lambda and theta are these things, then what will be the corresponding error in calculating the in the interplanar spacing. So twice d sin theta equals 10 lambda, this is the general formula, and for first order diffraction peak n equals to 1, so d equals to lambda by twice sin theta. Now take derivative with respect to lambda, del d by del lambda equals to 1 by 2 sin theta, and del d by del theta equals to minus lambda by 2 into cos theta by sin square theta. Now error in d can be calculated as, so this is the formula. Look, if we have some function f of x, y, and if has dependence on x and y, then we can write the error term like this. This is called propagation of errors. So you can check it out in Google or in any study material, you will get it. So you can write in this way: del t del lambda square sigma lambda means error square plus del t del theta square del theta is sigma theta square. So this is the error in determining d, and look, this d has dependence on lambda and theta, that's why we have taken these things. So by putting the values and del d square by d square, we have done this to find out the error in d. So we have done this just to simplify the calculations. Okay, now we get an expression like this, and all the other terms are known to us, or we have found out. D has been already found out here, and the other terms are given. So putting those values, we will get 1.1 into 10 to the minus 2 nanometer, which is matching with option 1. Question number 5, the dispersion relation of electrons in a 3-dimensional lattice in the tight bending approximation is given by Ek equals to alpha cos kxa plus beta cos kya plus gamma cos kza, where A is the lattice constant and alpha, beta, gamma are constant with dimensions of energy. The effective mass tensor at the corner of the first Boolean zone pi by A is. So to find out the effective mass tensor, we have to know what is that. So effective mass tensor is like this. So these are the components mxs star, mxy star, and similarly those other terms. Now mxx star means h car square by d square ek by dkx square, and the values are to be calculated at pi a, pi by a, pi by a, pi by a. So if we calculate this, we will get h car square by alpha a square, and mx y star equals to mx z square equal to 0 at pi by a, pi by a, pi by a, because those things will produce sine terms, and sine terms sine pi is 0. That's why these two terms are 0. So the first row is completed. For the next row, only the diagonal terms will survive and other terms will get vanished, and those things are calculated in the same way as this. Therefore, if we calculate it, you will get h car square by h square common, 1 by alpha, 1 by beta, 1 by gamma. The only diagonal terms are surviving, other terms are 0. So it is matching with option 3C. Question number 6. A thin metal film of dimension 2 mm by 2 mm contains 4 into 10 to the power 12 electrons. The magnitude of the Fermi wavevector of the system in the free electron approximation is. Now for 2 dimension, area of Fermi circle is pi into kf square, where kf is the Fermi wavevector, and number of quantum states in Fermi scale circle is n equals to 2 into L by 2 pi square into pi kf square. This multiplicative factor 2 has been introduced here due to spin of electrons, spin up and spin down. So we are writing L square as A area by 2 pi into kf square. Factor 2 is used for spin, as I have already told. So n by A means number of electrons per unit area. N by A equals to 1 by 2 pi kf square, and kf equals to 2 pi into n by A to the power half. Now n is given to be 4 into 10 to the power 12 number of electrons, 4 into 10 to the power 12, and area is also given. 2 mm by 2 mm means 4 into 10 to the power 6, so meter square. So you are getting it in meter inverse. So if you convert it into semi inverse, we get 2 pi into 10 to the power 7 centimeter inverse. Sorry, I have shown here the wrong answer, but this is the correct answer, 2 pi into 10 to the power 7. So it is matching with option 2. Option 4 is not the option. Sorry for this. Option 2 is the correct option. Option 2. Oh, this is wrong. Question number 7. For an electron moving through a one-dimensional periodic lattice of periodicity A, which of the following corresponds to an energy eigenfunction consistent with Bloch's theorem? So this question, for this question we have to use the properties of Bloch function. So for Bloch function, according to Bloch theorem, psi, the function psi, should be periodic. So psi of x plus a equal to psi x, where a is the periodicity. So only if we check this condition, you will see that only option 2 will satisfy this periodicity condition. Other options will not satisfy. Let me show you how it is satisfying. Psi of x plus a equals to, now in place of x we have introduced x plus a. We have placed x plus a in place of x, and we see that it is identical to psi x. So it is matching with option 2. Question number 8. X-ray of wavelength lambda equals to a is reflected from the 111 plane of a simple cubic lattice. If the lattice constant is a, the corresponding Bragg angle in radians is. So condition for of maxima for Bragg reflection is 2d sin theta equal lambda for first order reflection. So sin theta equals to a by 2d means we have put the value of d here, means 1 by root over h cut square plus k square plus l square by a square, and we are getting it at root 3 by 2. This is so straightforward. This is very simple question, but this type of question also comes in CSIR net exam part C. So you can easily grab 5 marks for such questions. So these are easy, and this type of things happen in this CSIR net June exam. questions like this, very simple questions like this came, and as a result of that we are expecting a higher cutoff. But that is different thing. Let's focus on this set only now. So question number 9. The critical magnetic fields of a superconductor at temperatures 4K and 8K means Kelvin are 11 milliampere per meter and 5.5 milliampere per meter respectively. The transition temperature is approximately, so we know that H of T, H means magnetic induction, or you can say magnetic field, H T0 1 minus T by Tc whole square, this is constant. So we are given the critical magnetic fields at two different temperatures T1 and T2. So we are writing the corresponding critical field for these two temperatures. Okay, so we are taking the we are dividing it basically. So 1 minus T1 by Tc whole square by 1 minus T2 by Tc whole square. Now putting the values of T1 and T2, and after simplifying a little bit, we are getting Tc equal to 10.583, that is approximately equal to 10.6 Kelvin, and it is matching with option 2. So straightforward question came. Now finally question number 10. The low energy electronic excitations in a two-dimensional sheet of graphene is given by Ek equals to h cut Vk, where V is the velocity of the excitations. The density of states is proportional to, so Ek is given h cut Vk, so B into P, because h cut K equals to P. P equals to E by V, dP equals to 1 by V dE, and density of states for 2D. This one you have already, this type of formula you have seen in statistical mechanics also. So Gp dP equals to 1 by h cut square 2 pi p dP. This is for momentum and this is for position coordinates. ds means area element. Okay, so GD, so we have just replaced P by the corresponding energy terms, and as a result of that, we look, d root integration of ds is a constant, so we have to know the proportionality. The density of this is proportional to, so it is proportional to the energy square. So it is matching with option 4. I have forgotten to mark it. Okay, anyway, so it is matching with option 4. So as you can see in your NET exam or in this type of different competitive exams, sometimes you can avoid complete calculation. Okay, they sometimes ask you about the dependence or ask you about the proportionality. So even if you don't calculate the whole calculation, you can predict the answer, you can correctly predict the answer. So this is all for today. So I would like to remember you that there are only a few months left for your exam, so be sincere and try to practice more questions. And if you have any confusion, query, you can comment down, and if you want to suggest me something about this video, or if you want me to suggest for any topic which I can consider to be the topic of my next video, you can comment down here. Comments on this video will be accepted, and I will try to make video on that. And if you are new here, please subscribe the channel and give a thumbs up, and don't forget to press the bell icon. And finally, thanks for watching.